Good morning. I hope you had a great holiday. Time to get back on track with our notes, and we're on the chapter of energy, work, energy, and power. So, conservation of energy. We've been talking about how energy is transformed from potential to kinetic and back to potential if we have something like a pendulum or a roller coaster, okay, going up and down. And so, what do we call that? So, it's the conservation of energy. So, conservation of energy. What does it mean to be conserved? Conserved means that the whole amount, the total amount, stays constant. Okay, it can change form. You can change potential energy to kinetic energy and back to potential. It changes form, but the total amount will stay the same. Mass and energy are both conserved. The total amount of mass and the total amount of energy on planet Earth or in a system stay the same. So, in this case, the light bulb breaks. Okay. When the light bulb breaks, the glass in the light bulb is a conserved quantity. Just because it's no longer in the light bulb form, it shatters on the floor. The amount of glass, the amount of metal on the inside and everything stays the same. It's just in a different form. Okay? Mechanical energy. So, what does that have to do with conservation? Well, mechanical energy is the total amount it's the sum of the kinetic energy and all the potential energies. Okay, whether it be elastic potential or whether it be gravitational potential. So it typically involves things that we can see. Non-mechanical would be things that we can't see, such as nuclear or chemical or electrical. So mechanical energy are things that you can see happening, the conversion. Okay. Mechanical energy is the sum of the kinetic energy, the energy of movement, plus the sum of all potential energies. Here's your equation: mechanical energy, kinetic plus the sum of the potentials. So thus far, energy, mechanical, non-mechanical. The types of mechanical energy are kinetic and potential, which we have talked about. And then potential can be broken down to either gravitational potential, like what you calculated on the worksheet yesterday, or elastic. This would be like the springs or the rubber bands. So, conservation of mechanical energy. In the absence of friction, we'll talk about friction in a minute. In the absence of friction, the total amount of mechanical energy in a system is conserved. Means it doesn't change. The initial mechanical energy equals the final mechanical energy. Okay? That means we don't lose energy. It can just be transformed from one form to another. The example: a pendulum is going back and forth. When it's at the highest point, it is not moving. It's 100% potential energy. As it swings down, the potential energy is being converted into kinetic energy. Remember the energy of movement. When it gets to the bottom, it is 100% kinetic energy. But it doesn't just end there. As it goes back the other way, okay, the kinetic energy is being converted back into potential energy because gravity is pulling on the plumb, on the bob at the bottom. So 100% potential swings down, 100% kinetic. It goes back up. The kinetic's being converted back into potential till it gets to the highest point, and it stops at the point that it stops. Before it starts to head back down, it's back to 100% potential. And then gravity is going to pull it down. Potential is converted back into kinetic until it's 100% kinetic. Then it goes back the other side and back and forth. Same thing would be with a roller coaster. Okay, 100% potential, roller coaster's car starts moving, goes to the bottom of the track, 100% kinetic, goes back the other side. But gravity is pulling on the car, slowing it down. And when it gets to the top, it comes to a stop. Okay? Doesn't have enough oomph to get over the next curve, the next hump. So, kinetic to potential, to kinetic to potential, kinetic to potential. You get the idea. Other than friction, mechanical energy is conserved in the presence of forces acting on an object. Okay? So the total amount of energy, the total amount does not change. It just goes back and forth into the two different forms. Mechanical energy is conserved when an object experiences variances in variable acceleration. So, again, it's slowing down. This is the pendulum. It speeds up as it's going down. It's going the fastest when the kinetic energy is 100% at the bottom. And then it starts going up the other side, and it starts to slow down because gravity is pulling it down. That's all this means. They just used more words than they needed. So, other than friction, mechanical energy is conserved in the presence of forces acting on the object. In our example, the forces are gravity. Okay? Mechanical energy conserved when an object experiences variable acceleration. The gravity is causing it to speed up on its way down because of acceleration due to gravity, 9.81 meters per second. But then gravity's pulling against it, causing it to slow down as the bob is going up. So, okay, friction. What's happening with friction? If it's totally conserved, what about friction? Mechanical energy is not conserved in the presence of friction. The total energy is still conserved. The total energy is always conserved. But the friction converts some of the mechanical energy into a non-mechanical energy such as sound or heat, mainly heat. So, you're sanding something, okay? You're going back and forth, back and forth. And so there is potential and there's kinetic, okay? The total energy is going to stay the same if friction takes some of this energy and creates heat with it. That's what it's saying. There you go. So, as whatever he's holding, I think it's either sandpaper or a mouse, I can't tell. As it goes back and forth, a portion of the mechanical energy or the energy of the movement is given off as heat. The total amount is conserved. The total amount of just the mechanical is not. And that's it. So I mainly wanted you to get the idea that the total energy in a system is conserved. It can go from one form to the next, kinetic to potential, but the total amount is conserved, even in the presence of friction. Some of it will be calculating friction in a little while. But friction still is part of the system. So it's not lost. The total amount just goes into a different form. Now, the mechanical is just the part that you can see the kinetic to potential and back. The mechanical energy does not include friction. So hopefully that's not too confusing. Get your notes done in your journal, take a picture, and send them to me. Thanks, guys.